In this video, we're going to be going over the A-star algorithm for graphs. So the A-star algorithm is actually just a slight variation of Dijkstra's. So we're going to start with understanding Dijkstra's. We're not going to be going quite down to even the pseudocode level when we talk about A-star because we're just trying to understand it for some breadth to understand some other algorithms related to Dijkstra's. Or similar to Dijkstra's. So we're going to do that through a visual interpretation of a graph as a grid. So this grid is going to be our graph, and there's not going to be any weights. We're just going to use an unweighted graph, so all edges are the same. And we're trying to find the shortest distance between the two stars. So if we were to apply Dijkstra's and go from the star on the left to the star on the right, it would look something like this if we visualized it. Oh, okay. So what it's going to do is Dijkstra's is going to do this sort of like breadth first search, right? Because there's like no difference between any of the nodes in this particular graph because there's no different weights. So it's going to look very much like breadth first search. It's going to just kind of explore radially until it hits the star. You can think of the green cells as cells that have been visited, and you can think of the red cells as cells that are basically in the queue, in the priority queue. And the idea of Dijkstra's is great, but what it doesn't do is it'll search in directions that make no sense. So Dijkstra's is going to go off to the left and search even though we're searching to the right of the graph, right? So the element that we're looking for is on the right, and so we aren't taking into account any other information about the graph. We're just, looking greedily from the exact node that we're at out. So the way that Dijkstra's prioritizes the order that it visits nodes is just the distance between the node that you're at and the node that you're visiting. So the node that you're at S and the node that you're visiting U. But it doesn't take anything else into account. So ideally what we might want to do is include a second component to the priority that takes into account some other information about the graph that could make a smarter decision. So you could just think of it as future costs, like something that can tell you something a little bit more informative about this choice that you're making. It's a little bit more complicated than what's here, but this is just to get you a basic idea, so this is going to continue to be revised as we go on. But the idea is that you're just adding something to the priority that's a little bit more informative. So for example, let's say that we take into account the distance that the node that you're exploring is from the node that you're trying to get to, and you include that in the priority. So nodes that are less far away from the node that you're trying to get to are prioritized first. If you did something like that, this is what the exploration would look like. It's going to make its way right to the star because it knows that as it's exploring, continuing to go right is going to get you there faster. So you can see that there's this additional calculation. So it's 3 away from the star, but it's also 4 away from where you're trying to get. So as you keep adding this component into the priority, it starts off as 1 away from where you started, but it's 6 away from where you're going. This is the basic idea that you can use to improve the algorithm. So it's not quite that easy because oftentimes you don't know that you're actually connected in that way, and it might be hard to determine what the connection is. So as just like an example of how to think about this with this grid example that we're using, let's just say that there's something blocking the path. So the path isn't a direct path from, this star to this star, right? You can't just go straight through here. There's some sort of block here. It's analogous to a graph that, you don't actually know that this node connects to this node or something. So how do you actually determine how close a node is? Well, the idea is that what we're going to do is this future cost, we're going to call that a heuristic. And what it is, it's an underestimate of the future cost. So assuming that block is there, assuming that there is no block there, what would be like the smallest possible distance that it could be? And that actually does a really good job of improving the efficiency of the algorithm. And what it does is it allows you to get rid of like very terrible paths. So under the best case scenario, this path is still terrible, is the idea of this heuristic. And I'm going to show it with this really simple idea of a distance to the final node, but it could really be anything. So an admissible heuristic is a heuristic that always underestimates the true cost. So what that means is that as we're looking at this path, if we're exploring this node, we know that it could be no better than 4 away or 3 away, right? That would be underestimating the possible distance from the node you're exploring and the node that you're trying to get to. And that's the basic idea of this heuristic. So we're going to add that to the priority. So we're going to take the distance as is, but we're also going to add up this heuristic, which is a underestimate of the possible true cost that it could be, right? So what we're going to use as our heuristic in this example, which, is just an example of how this might be implemented, is what is known as the Manhattan distance. So if we're exploring this node here in blue, the Manhattan distance is just the number of columns it is apart and rows it is apart from the node that you're trying to get to. It's called the Manhattan distance because if you're in Manhattan and you're trying to get from point A to point B, Manhattan is a grid, and so it's the way that you would travel. And so we're going to use this as our heuristic. And again, we're going to assume the best possible scenario so that it's the shortest distance regardless of what might be in the way. The idea of the admissible heuristic is that as we're exploring, even in the best case, this path here that we've added to the queue is still bad, right? There's other paths that are better. So this is 11, but we know that we've already found a path over here that's 9, right? If we just used Dijkstra's, we would only know about 3 and 7, right? We know this is 3 away and this is 7 away. So it wouldn't tell us enough to know which way to go. But if we add in this heuristic as we're exploring, it allows us to better decide which path is better to prioritize. So Dijkstra's algorithm is written here. This is just pseudocode for what we've already kind of talked about. And Astar is actually exactly the same, but it just adds on that heuristic. And it could be anything. So the Manhattan distance isn't the one, but it's just an example of one. So it gives better priority by using other pieces of information about the choice. So if you apply Astar to this example that we've been using, you'll see that it prioritizes to the right and it kind of makes its way around the block and it avoids radially navigating out because it's finding better options as it goes right, and it eventually gets there more efficiently than Dijkstra's. So this is a ending screenshot of all of the nodes that are visited with Astar, which would be in green, and then all the yellow nodes are things that are still in the queue, and then all of the nodes that are visited and still in the queue with Dijkstra's. And so you can see how much more efficient Astar is. So you might be wondering, why do you underestimate? So you only ignore paths that in the best case are worse than your current path. And so when we went back here, we're ignoring this path because in the best case, you have better options than that path, so you just get rid of them. And the choice of heuristic is important. If you want to think about all the options of this heuristic value, so what you add on here to the priority, if you were just to set that to 0, Astar is going to become Dijkstra's. If you underestimate, this is going to be the same or faster than Dijkstra's, and it will find the shortest path, assuming that you use an admissible heuristic. There's also this idea that you use a heuristic that's perfect, so one that can tell you exactly what you're looking for. That will be able to find the best path, but and it will find it fastest, but it requires perfect knowledge of the graph, which is typically not something that you have. And then if you overestimate, it won't actually necessarily find the shortest path, because it's basically going to give everyone the same priority and you won't really get any advantage. So using the underestimate is what's really going to help you here. But it might run faster, but it won't necessarily find the shortest path. So remember, an admissible heuristic is the key to A star. It's the only thing that's added to Dijkstra's. It's just this really simple addition in the algorithm. You know, the actual heuristic itself is not simple. And it is something that always underestimates the true cost of the choice. So that's a little bit about A star, which is more of an advanced algorithm that you kind of explore after understanding Dijkstra's.